Alors, j'ai le plaisir de vous présenter Reinhard von Hanxleden, qui est professeur à l'université de Kiel et qui travaille depuis très très longtemps avec son groupe sur Esterel, ses applications, son enseignement et ses améliorations à travers des nouveaux langages qui reprennent les principes mais les remettent dans des contextes plus classiques. Par exemple, et il travaille aussi beaucoup avec des gens plus classiques, comme les gens des automates programmables, des automatismes, etc., qui ne sont pas du tout habitués au concept que j'ai montré, quoique ça dépend. Et il essaye, vous allez voir, je vous laisse. Il a fait beaucoup de réalisations avec son équipe, que je ne sais pas ce qu'il va vous raconter, c'est lui qui va le savoir.
Merci Gérard. Bonjour à tous. Merci beaucoup pour cette invitation. J'ai accepté avec plaisir. But now I will not expose you to my English anymore. It's difficult enough to speak after Gérard Berry as it is, so I hope everybody is fine with that. I'm sure your English is better than my French. So I think the main part of my talk will be about explaining what the title is, Sequential Constructiveness, SCL and ScCharts. And as Gérard said, the subtitle explains it a bit more. So it's about adopting some of the concepts of traditional languages, or more specifically imperative languages, to the world of synchronous programming. So just to start at the beginning, this is about reactive systems programming, like traditional synchronous languages as well, meaning that we have some system like a pacemaker or something that continuously reacts to some environment. So we have some sensor inputs that are read from the environment. Then we have some computation, and then we write some sensor outputs to the environment. And in between, we pause. So the Esterel pause instruction morally means the passage of physical time. So I think this is pretty much the standard setting. There's a slightly more subtle message here, meaning that the pause should really be about passing physical time. It should not be about scheduling computations in here. So, for example, you should not have to use the pre-operator to distinguish two different values of a variable or of a valued signal. So we really want the pause to be for physical time. And so that's why we put it there. And now what my talk will be about, to discuss a bit more about how you specify the computation in there. And so the mode of computation that I will explain is about this orange part here, and I will discuss some language dialects that are about expressing what is happening in there. And so all this is a conservative extension of the synchronous mode of computation. So what you were allowed to do before, for example in Esterel, you are still allowed in this new extended mechanism, but you are allowed to do a few more things in addition to that. So the family of languages that I will concentrate now for describing this orange part, this computation, is from the state charts family of languages. So far you have seen mostly textual languages like Esterel and maybe a bit of Listre, but there are of course also these graphical languages, and in this case in particular state charts. And state charts have been invented quite a while ago by David Terrell. So may I ask here in this group, I can't ask you on the internet, so who has been a bit familiar with state charts? Who's heard of that? Yeah, some, a little bit. Okay, you talked about that already, great. Okay, so just very briefly, state charts are basically an extension of finite automata where you have some different states and you have some transitions between the states. The extension is that you also have concurrency, here indicated with this dashed line. So you have two concurrent regions of activity, just like with a parallel operator in Esterel. And we also have hierarchy. So, for example, if some event A happens, then we leave this complete superstate here. We do not have to add such transitions from every single state, but we just draw one superstate and we leave out of that. So that was a very popular mechanism from the beginning on. Application engineers loved it because they could express right away what they meant, even very complicated things or simple things like this wristwatch. And computer scientists also loved it because they recognized, well, there is a pretty clear intuitive meaning of all this, but what it really means in detail is not all that clear. And so, for example, Michael von der Beek, he fairly shortly after the first original state chart proposal, compared the different state chart variants that were known until then. So he had 21 different semantic variations of more or less the same syntax. So for example, whether they're graphical or textual, whether they allowed reaction to absence or not, and some more things. And this is just the tip of the iceberg. So this whole table looked like this. So there are many different criteria in which we have variation points of what these state charts actually mean. And there, of course, he included also the original state chart semantics from David Turrell, or at least he thought so, because then shortly after this paper came out, then David came along and said, no, 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 you got it all wrong. What I actually meant is this. And he came up with a further paper and a 20-second column for all this, explaining in more detail what he really meant the state charts language to be about. So there was a lot of chaos there, and this does not even include the languages that we have today, like, for example, the state flow dialect or the UML state charts. And there came certain order into this chaos with the synchronous languages. So in particular, Florence Maraninci, together with Nicolas Halbwachs in Grenoble, they proposed a first synchronous version of state charts called Argos back then. And this has been developed further into the ScCharts language by Charles André. And so, even though some might disagree a bit, but more or less you could say it's a graphical variant of Esterel. So you have, for example, the concepts of weak and strong boards, and the other concepts that you have in Esterel you can also express there. So that's basically the setting that we are in now. This has worked quite well, and for example, this has also been commercialized in the Esterel Studio tool, and in a certain variation, you also now have some of that semantics also in the SCA tool. And so the question is, well, isn't it everything perfect then? Why do we have to do anything further? So what is the motivation for doing more than what we have there? So now let me get a bit into the motivation. Why would one want to go beyond what we have there? So there are certain limitations, at least at the programming level, of what you can do right away in the synchronous setting. And in particular, if you're coming from a standard traditional imperative programming background, there are certain things. For example, look at this innocuous piece of code. So assume that this is a piece of C code or a piece of Java code where you read a variable x, and if this variable x is false, then you do something and then you set it to true afterwards. So this is fairly common, for example, in control algorithms that, for example, you detect whether a certain task has already been finished. If it has not been finished yet, then you do something and you finish it. So if you look at this as a C program, this is perfectly okay. A C compiler will accept it, and a C programmer will be used to the ability to write such programs. Now things are a little different in the synchronous setting. So for example, if we interpret this now as a sync chart, more or less, where we have some initial state here and another state there, and we say we take a transition from here to there if x is false, and if so, then we set x to true. This would be the morally equivalent sync chart to what we just saw earlier. Then this is not a valid sync chart. It's not accepted because it does not adhere to the principle that each value here should be unique within a tick. Because this computation here happens instantaneously. It does not consume time. So there, in the synchronous setting, there's the requirement that, for example, a signal is only present or absent within a tick, not both at the same time, not considering schizophrenia that we heard about earlier. But here we actually have two different things. There are first false, and then in this case, possibly true. And while on the one hand, there are very good reasons for requiring unique signal values. For example, if you take the circuit view, then each wire within a clock circuit, within a clock cycle, should have only the unique value of high or low, present or absent. It should not be both at the same time. It should stabilize to a well-defined value. So there's a good reason for that in the circuit world. But for the programmer world, In this case, there is not really any ambiguity here. For example, there is no race condition. So usually a strength of synchronous languages is, for example, that you do not have race conditions even if you have concurrency. There are no write-write races or write-read races. It does not depend, for example, on a Java scheduler, what result you have if you have concurrent threads. But in this case, there is not even any concurrency. So it's just normal sequential behavior here. There cannot be any uncertainty, there cannot be any non-determinism, so there is no reason why this should be rejected. And that's actually the motivation for this work, that we want to accept this as an SC chart. And you can also play the same game on the Esterel side. If you look at this as an Esterel program, assuming that there are no other emitters of X, if you write something like that, if X is present, do nothing, but if it is absent, then emit X. This would also not be a valid Esterel program. But in our conservative extension that takes sequential control flow into account, then we say, well, it's actually okay for the same reasons as before, because we have a clear deterministic order of execution here. So again, this is a conservative extension. Esterel programs that have been valid are still valid sequentially constructive Esterel programs, and they have the same meaning, but we accept a bit more. And in particular, we accept those programs that are used for which the traditional imperative programmer is used to being good programs. We also want to accept these. So that's the bottom line. By the way, feel free to jump in at any point in this presentation. So I'm fairly flexible with how much or how little I talk. So I understand we have a hard deadline that the doors close at 7 p.m. And I will finish well before then. So feel free to ask any questions in between. So I'm happy to do this a bit interactive. So we want to preserve the nice properties of synchronous programming. We want to preserve determinacy, we want to have a sound semantic basis, and we want to have efficient synthesis. But we want to reduce the pain, and especially of teaching the language to new programmers. So I've also been teaching this now for a number of years to people who come from this imperative background. And yeah, sometimes there is a fairly steep learning curve, and I think there will still be a learning curve also with this. It's still fairly easy to shoot yourself in the foot with this, but it's not as easy as it has been before. So we want to make this easy to the mainstream programmer, and we want to reject only models where determinacy is compromised. That's the bottom line. So I will now talk a bit about the model of computation that we use. So that's looking a bit at the foundations. And in a later part of the talk, I will look at how we practically use this. I will also talk about textual and graphical languages. I mentioned that we now look mostly at the graphical SC language, but we also want to use some advantage of textual languages. And then I will talk a bit later about data flow aspects. This now is mostly control-oriented. You know, traditionally there has been this distinction between control-oriented languages like Esterel and ScCharts, and on the other hand, data flow-oriented languages like Lustre and traditional Skate. And I will talk a bit about comparing these two. And that will be mostly the structure of my presentation. So, model of computation. So, in sequential constructiveness, we want to extend a bit the traditional write before read requirement. So in Esterel, you have this rule that if a signal is emitted and if it is tested with a present test, then it first has to be emitted before it is tested, to forbid that first we test a signal to be absent and then we emit it, it becomes present. Again, so that you have a unique present status of the signal throughout a tick. So we still have that requirement, but only under certain circumstances. And in particular, we do not have this requirement if there's clear sequential control flow in the program. So in particular, writes are visible only to reads that are either sequentially later, so they don't consider sequential predecessors, or they are concurrent. So write before read, the traditional Esterel rule only applies under certain circumstances. So to refine that a little bit, it's all about scheduling variable accesses within a reaction. And so in particular, if we have sequential accesses to some variable, we do not have any constraints. Then we assume that the programmer knows what the programmer wants to do and expresses that in sequential control flow. If there are concurrent accesses to a variable, then we have a certain protocol that this should obey to, in which these accesses should be scheduled. And we call this IUR protocol for reasons that should become clear in a minute. So we first have any initializations. For example, if we set x to a certain value, we call that an initialization. Then we have what we call updates. So for example, here we add 2 to the value of x, and here we add 5 to the value of x. So if you know Esterel combination functions, that's basically it, using a combine operator, in this case plus. So typically this is a commutative and associative operator, like logical OR, for example, or maximum. So we have these 2 different types of writes to x. And then finally we have reads to x. So here we assign x to y or x to z. So whenever we have concurrent accesses to some variable, it has to adhere to this initialize, update, read protocol. So that's the rule. Okay. And we still can have causality cycles, just like in Esterel, and then the compiler must reject those. So for example, if we have 2 concurrent threads, and one thread wants to set x to 1, and the other thread wants to set x to 2, we still say it's a bad program, and the compiler rejects it, and we still have a write-write race condition in this case. So the idea of this now is fairly simple, I think, just like in the example that I showed you earlier. But it has turned out surprisingly tricky to formalize this. And I guess Gérard has known this all along and could have told us that also right away. But we were a bit surprised. We meaning, in this case, for example, in particular, my colleague Michael Mendler from Bamberg University and myself. So when we tried to formalize this seemingly simple idea, it turned out to be fairly tricky, and so what we came up with first was this definition. We say that a program is sequentially constructive if there exist runs obeying the IUR protocol. So what does that mean? So a run is a certain execution of our program, and obeying the IUR protocol means that whenever we have concurrent accesses to a variable, that they obey this first initialize, then update, then read order. And we would have actually liked to stop there, meaning we would have liked that if we have this, this property of a program, that there exist such runs that obey the IUR protocol, that then already we have a well-defined semantics. However, it turns out that there are programs which do fulfill this property, but where the result is still not well defined. And so we actually had to add a second rule that all such results, all such runs produce the same result. So this corresponds a bit to the logical correctness requirement in Esterel program, that a program first has to be deterministic and it has to be reactive. There's that analogy. So that's, I think, a working definition, and we have formalized all that, and all is well. However, we were not entirely happy with this yet, because this definition, on the one hand, is not really tractable to compute statically by a compiler. You have to look at all these different runs, so that does not scale. And on the other hand, it permits certain programs that we call speculative, meaning that you kind of have to take a leap of faith when executing a program. And so they are not really constructive in the sense of constructive Esterel programs. So now in a more recent definition, in a more recent development, we say a program is SCC if it corresponds to a sequentially constructive circuit. So we have come up with a circuit semantics, which is quite similar to the Esterel circuit semantics. It mainly differs in the way how signals are scoped. And so here again, we are in the nice world of physics, where we say a program is well-defined, it's sequentially constructive if and only if it corresponds to a hardware circuit that has a well-defined meaning, meaning that for all inputs, for all possible executions, all signal wires always stabilize to a well-defined value after a finite time, irrespective of how the hardware is realized, meaning irrespective of how much delay a certain logical gate has. Okay, so one way of putting it is, well, it fulfills this, and in addition, it does not speculate. Okay, so for the rest of this talk, it does not really matter which definition you adhere to. This just to give you an idea that there are different levels of strictness of what we allow. So this is the looser definition, this is the tighter definition. And I will also display this in some other way if you look at different program classes. And here I look at programs, Esterel programs again. So first of all, we have the class of what we call Berry constructive programs. So they correspond to the constructive semantics of Esterel. And so, for example, here we have a little example where we have two signals A and B. And the kind of tricky part here is that B depends on A or A depends on B, depending on whether some input signal is present or not. So in general, we have a kind of problem when we have this circular signal dependency, but in this case it's okay because this input signal I must be well defined in any case. And then here, if A or B is present, then we emit some O. So this is okay, this is a valid Esterel program. We have this other class of programs to which this program does not depend, which is acyclic, meaning roughly that we do not have any cyclic dependency of the signals, just like here, the cyclic dependency between A and B. So here, for example, we say if S is present, then we emit T, then we emit S, and then again we check whether S is present or not, and if so, then we emit U. And as you see here, this off-on example is not Berry constructive, because in this case, we first check the presence of S and then we emit it. So a traditional Esterel compiler will reject this. Okay. And then we have the intersection of these two classes. So if you look at this simple program, we emit some X, and concurrently, if X is present, then we emit some Y. So these are three different types of program classes. And we can distinguish them, for example, by what class of programs can be handled by what compilers. So most Esterel compilers compile this kind of program class. There are some Esterel compilers that also compile these programs. So for example, if you look at the Esterel v5 compiler with causality analysis, it will also accept this program class. And now what we are about mainly is to also compile this kind of program. So for practical purposes, we want to extend this class of programs that can be compiled to this class of programs. And if you do full causality analysis, then also we want to compile these classes of programs. Okay. So if we go beyond the world of Berry constructive and acyclic programs, then we come to this SCC class of programs that I mentioned a minute ago, which correspond to a sequentially constructive circuit. So here we have an example where we have a loop, where first we emit some signal S. If I is present, then we pause. Then we check S, and if S is present, then we emit T. And then if I is absent, then we pause. So this is not an instantaneous loop, because no matter what value I has, we always pause. So in that respect, it's okay. But here it's a bit tricky, because either S is executed within one tick after the emit, if we do not execute this pause, or this present S is executed before the emit, if we do not execute this pause. So here we have this cyclic scheduling issue, and we cannot say at compile time whether we first have this statement and this statement or the other way around. But it's still sequentially constructive, depending on whether you execute this pause or not. This S is either present or absent. Okay. And then furthermore, I said we have this looser class of programs that permit speculation. So if we look at this module here, x, y, so we say if x is present, then we emit y, and conversely, if y is present, then we emit x. So if we look at the dynamic interpretation of this, we always assume signals to be absent initially. So in this case, we somehow have to choose whether we first want to execute this or this. If we first execute this, present x, well, x is absent. Therefore, we do not emit y. Next, we execute this. Well, y is not emitted, so it is also absent. So we have x also not emitted. So then we have the result, x is absent and y is absent. And we also obey the IUR protocol because we, in this case, do not have any concurrent write and read because none of the emits is executed. And if we take the other scheduling choice, if we first execute this one and then this one, we get the same result. X and Y are absent. So this is sequentially constructive, in that we have runs that obey the IUR protocol and all the runs lead to the same result. But we somehow have to take a leap of faith when we start executing any of these. For example, if we execute this, then we kind of have to speculate on the fact that this X is not executed. And why should this not be executed? Well, because this is not executed, or this is considered absent. And why is it considered absent? Well, because this is not executed. So before we even go into this, we kind of have to know that we do not execute this branch. And so that's the speculative bit. And so, for example, if you construct a circuit according to the Esterel circuit rules, this circuit is not guaranteed to stabilize. Okay? You can assign certain gate delays so that this circuit will oscillate. And that's why, actually, personally, I do not like this kind of program very much, and why I personally prefer this class of programs. Okay? And then, of course, there are some programs that are even outside of this. For example, here, if X is present, then we emit Y, and here, if Y is absent, then we emit X. Well, there's just no good assignment to this. No matter what you do, you will have an inconsistent signal assignment. So if you assume X to be absent and do not emit Y, then you check Y here to be absent and you emit X, and so that violates your assumption that X has been present. And if, on the other hand, you assume that X is present, then you emit this, and therefore you do not emit X. So again, your assumption fails, so this is just a bad program. So we do not want to deal with this kind of program. So this is now very roughly the setting that we are dealing with. We basically want to extend this class of programs, the very constructive programs, to this class of programs, or if you wish, also this class of programs. Okay. All right. Any questions on this before I go further into discussing the ScCharts language? No. Okay. So we have actually different types of language, and let me start basically with the hello world of synchronous programming. So we have the ABRO program with a certain interface. We allow some initialization. And in this case, we are working with Booleans, not with signals. So the basic mechanism that we work with are not signals, but instead variables that persist from one tick to the next. So that's one thing to keep in mind, even though we will later see how we can recover signals also using the variable mechanism. we have a superstate, and the superstate in this case has one region. Here is another superstate that has two concurrent regions. We have in each region an initial state. We have a final state shown with this double outline. Initial states have this solid outline. We have a so-called delayed transition, showed with a solid arrow. We also, in addition, we have the immediate transitions. In ScCharts, they are shown with a hash mark. Here we use instead the dashed line syntax. So this distinction between delayed and immediate, you may already be familiar with. It's like the difference between the await and the immediate await. So this transition is only considered after the initial tick in which this state has been entered, whereas this immediate transition is considered right away, also from the first tick onwards. We also have a strong abort, and here we have a termination. So most of the syntax of that is just like in ScCharts. And now one of the things about ScCharts is that it is built on very few, very small building blocks. These are 5 building blocks. And these are a region which has one initial state and an arbitrary number of final states. We have a trigger, meaning that we have either a condition that is true, then we take this transition, or else we take this default transition. So these numbers denote priorities, the order in which triggers are tested. Then we have an effect, shown after the slash. We have a superstate with an arbitrary number of concurrent regions. And then finally we have the state, and that's the only one that has a delayed outgoing transition. So these are all immediate transitions. These are delayed transitions here. So these can be mapped, these so-called normalized core ScCharts, to a different language, a low-level language if you wish, called the Sequential Constructive Language, SCL. So for example, a thread is graphically corresponding to some entry and some exit state. So this is the Sequential Constructive Graph language. We have a conditional, we have an assignment, and so these 3 are basically like standard control flow diagrams. And then the extension to standard control flow diagrams is that on the one hand we have concurrency, denoted with fork, par, join, and we have the pause statement. So you already heard about the surface and the depth of a pause statement. So here you see it explicitly, the surface in which one tick ends and which is executed the first time that you execute a pause, and the depth, which is basically the second half of the pause statement from which you resume. Okay, and so if you look further now upstream from this, we have the so-called core ScCharts with basically the standard building blocks that you already saw. I won't go through them in detail again. And on top of that, you have the extended ScCharts, and these have things, for example, like the abort statements. And so the basic idea of this is that you can go from this to these very simple building blocks at the bottom just through a series of model-to-model transformations. So as a simple example, here we have the ABRO example again, but in this case using signals. And we can apply a series of compilation steps. So this is actually shown in the Kiel tool that we use to experiment with, and also to experiment with the compilation. And a bit later, I will also show this in the tool. So if we step through this, the first thing that we do is that we compile the signals away. So replacing the signals by Booleans. And in this case, we also have an immediate during action which initializes the Boolean O, the output signal O, or the output Boolean of O to false. So this corresponds to the fact that a signal is initialized to absent at each tick. So we interpret false as absent and true as present. And furthermore, this emission of O is replaced by this assignment where we say O equals true. except we do not say quite O equals true, but instead we say O or equals true. So this bar is just like the bitwise or in C or Java, or like the non-short circuit or in Java. And so this here is corresponding to setting O to present. So now one question is, for example, why do we write it this way? Why don't we just set it to true? And another question is, well, if we want to execute this, well, what do we do first? Do we first want to set it to false? Do we first want to execute this? Or do we first want to set it to true? So in a way, we also have a race condition there. And while the answer to both questions is, well, we use this initialize, update, read protocol, because this is an initialization to false, and this is an update, because we use this logical OR here as a combination function. So this is where the sequential constructive protocol tells us what to do. First initialize to false, and then we set it to true. Okay, and actually, the desire to encode signals using variables was also the major motivation for using this initialize, update, read protocol here. So once we have done this model-to-model transformation, then we next want to compile this. So this is the signal transformation. Then we want to compile the during action away. So this now corresponds to a concurrent region where we always initialize O to false in each tick. So now we've come a little closer to the core ScCharts. The next thing is that we want to compile the abort away. So here we have this strong abort, and we do not have this abort in our core language. So therefore, we just use a normal termination here, but we check at each state whether the abort triggered by the input R has to be taken or not. And this is actually something superfluous here, because sometimes when we want to handle more complex abort patterns, then we have to check whether the whole superstate terminates or not. So this could actually be, this is not necessary here. And so now we are almost at the core ScCharts, except that here we have this connector, which can be compiled away into a simple state. And then we are at the core ScChart level. So now we are basically one level down in the big picture. But this is still not quite the normalized core ScChart level that I showed earlier, for example, because here we have delayed transitions together with a trigger. And so we have to take these apart. Basically, we take apart surfaces and depths. And now we are actually at the normalized core ScChart level. And now we can make a one-to-one transformation to this low-level format that I showed. So first, let's look at this in a bit more detail. That is shown here. For example, in the handle A region, we first take a transition to here, a delay transition, because we do not immediately check for A, but we want to check for A in the next tick. But first, we have to check for the reset. If the reset takes place, then we enter the final state. If not, we go to here and we check whether A has occurred. If so, then we terminate also. Otherwise, we go back. Okay, so that's the normal behavior. For example, in Esterel, you would write await A to have this semantics here. Okay, and now this thing can be translated directly to the SCG, which is this. Here we have two concurrent regions, and here again we have two concurrent regions, and again two concurrent regions. And what we see here is, for example, that O is initialized to false. Here O is updated to true, and this blue edge means that we have a scheduling requirement, that first we want to schedule this, and then we want to schedule that. So on the one hand, we have the sequential control flow that governs our schedule, and on the other hand, we have this concurrent communication that governs our control flow. So if we take stock so far, we have defined ScCharts by a series of model-to-model transformations. So first we have extended ScCharts, then we have core ScCharts, and we have normalized core ScCharts, and then at the end we have the SCL and the SCG. So I also have something on the further downstream compilation. If you're interested, I can show that later, but for now let's skip over that and let me go a bit to the pragmatics side. So we discussed the semantics, we discussed the syntax, and now the third one is the pragmatics of how we actually deal with this language. In practice, how can we work effectively with this? That's one thing that we've been pursuing for some time, in particular for model-driven engineering. How can we save developers' time? And one guiding principle we use here is the model view controller paradigm, which has been well known in software engineering. And so now this is from the original paper by Trygve Renskog. I'm sure I'm butchering the pronunciation there. Now some almost 40 years ago. So he said, a model represents knowledge. A view is a visual representation of its model. It would ordinarily highlight certain attributes of the model and suppress others, thus acting as a presentation filter. In other words, the view should not always show everything. It should just show certain things that you're interested in. And then the controller is the link between a user and the system. It provides the user with input by arranging for relevant views to present themselves in appropriate places on the screen. Well, I read this to mean you should do your layout automatically of a graphical model. It should not be done by the user. So if you have worked with graphical languages, then you may have noticed a certain pain with rearranging things. It's like writing PowerPoint slides. It's a very time-consuming process, and we want to do this automatically. So what does it mean for us when we work with ScCharts? We want to express the model textually. So for example, the ABRO, if we write that, we do not draw things on a canvas, but instead we write a text file where we first have the interface, then we have our AB, then O state. If R is present, then we abort to this. That's the self-transition. Then we have our initial state, weight A and B. If we join that, then we go to the done state, which is the final state, and we emit O. We have a region handle A with an initial state and a final state, and similarly we have a region handle B with an initial state and a final state. So why do we do this? Well, it's for efficiency. As I said, that's the motivation of pragmatics. There are other things. For example, if you want to difference models, it's a lot more difficult to do this on visual models than on graphical model, than on textual models. And also revision control, if you want to see how does a model evolve over time. The view is automatically synthesized by the Kiel tool that I already mentioned. So that's the controller. So that is customizable, and again, the idea is to save developer time. So we have basically different levels here. On the one hand, we have the ScCharts world, and that is using, or that is prototype now within Kieler, and Kieler again uses the Eclipse layout kernel for automatic layout. And this is all open source, available under a fairly free license, Eclipse public license, which also allows, for example, commercial use. So if at the end of this talk you think, well, the semantics is all nice, but what really interests me is the automatic layout, then you can use just this without using any of the other things. For example, if you use Ptolemy from UC Berkeley, that also uses ELK, even though they are not based on Eclipse and just are using pure Java. Okay, so now let me show this a bit in the tool, because it's easier, I think, to see there than if you see it at all. Yes, there we go. This is a bit big. Okay. Actually, for that, let me synchronize the screens. That's a bit easier. Okay, so here on the left side we have the textual model, That's the ABRO that we just went through. And on the right side, we here have this automatically synthesized diagram. And as I said, the views should be customizable. So you can, for example, say you have a very complex model, a lot bigger than this, for example, then you can collapse a certain part of the model so that you are just seeing the outside of it. Or you can, for example, if you have a very big interface, a very big declaration there, then you can, for example, hide the declaration. So now if you watch this, if I unclick this, then the declaration disappears. We can also use this for the navigation, except that the labels have disappeared. Okay, sorry about that. Okay, well, okay, that's always the thing if you show things live. But I also have it on the slides. But let me try this again. So there you also see a little outline of the Baltic Sea that is going to Kiel with the different ferry stations. So that's where the splash screen comes from. Okay, so if we have here, for example, again, our graphical model, we can also use this to navigate from the graphical model to the textual model. So for example, if I select this region here, then it's shown automatically in the text. Or if I show this transition here, then again, we see what part of the transition is shown there. And now, for example, assume that you do not want to have just one handle B region, but you want to have several of them, then you just edit the source and you have a third region here. Or if you want to have a few more, then again, you have a few more of these regions. And if you explain this to somebody who is used to textual modeling or textual programming, and if you show them in the textual editor, hey, look, I can just copy things multiple times. They look at you and say, well, okay, so what? I'm doing that all the time. But if you show that to somebody who is used to graphical modeling, show that you can go from one region, handle B, to 8 regions of handle B, they again just look at you because they say, well, that's not really possible usually. Usually it really takes you a long time to go from the ABRO that I showed you earlier to the ABRO that is done there. So now let's just undo this so that we have the original one. Okay, and so now we are back to that. We can also, for example, play around with different layouts here. So this is the default, or in this case, we have everything laid out to the right. We can also lay things out vertically like that, or we can alternate between a just vertical and then horizontal and then vertical layout again, or we can do it the other way around. So that's the idea, that you can have different views of one of the same model. So the model is done with the textual editing and the views are synthesized, in this case, by the Kiel controller. Okay. All right, so we just went through that. So also I'm happy to make these slides available afterwards. Okay, so we can also simulate. So in this case, for example, we see the different values of A, B, R, and O down here. We also see the current values. If we start the simulation, we see everything is initially false. Next, I set the input, the signal A, to true, and I take this transition. I can also then next go set B to true, and so in this case this whole thing terminates and I go to the done state, and then I can reset this again. Okay, and so we have tested this also with fairly large models. So for example, this is a railway project that we regularly perform, And so this has been a fairly substantial SC chart. This now generated lots and lots of code. So these results are now 2 years old. So since then we have experimented with more compact code generation schemes. So this is basically based on macro expanding everything, just like you would do for a hardware circuit. We also have an alternative implementation, which is more software-like, where we reuse components. The compile time, well, about 2 minutes. But what we have been quite happy with is the reaction time. So from the beginning on, speed was not a problem, even though the program was quite big. Okay, so much about that part. Any questions on this? No? Okay, now as I said, let's go a bit into the data flow side. So again, our SC chart is usually control-oriented. And there's not a lot of data flow here, but we can show a bit, for example, if we are interested in, well, what data flow into the different regions. So for example, in this region here, there flows the input R, this is reading R. And this region here is reading A, and this region is using B. So again, let me show that in the tool. It's a bit nicer there. So let me go to, okay, that layout direction is fine. So now if I go on induced data flow, and I want to see the local variables, then I see, okay, that's basically what we just saw on the slide. So again, this is just using the same textual model. I did not add anything to that. I did not have to write a separate data flow model. Or if I want to show all inputs, including the ones that are used internally, then I see all the inputs A, B, and R here, and I see the output O there. So that is not very interesting in this case, but let me look at a different example that is slightly more interesting. So I want to collapse all regions on this, and let me first switch off the data flow view. So here we have 3 concurrent regions, one that sets the speed, one that controls a motor, and one that simulates the time. And let me get rid of the declarations because they take too much space. That's up here, there. Okay, so at this point, I see the traditional control flow-oriented view, meaning we do not see anything of what's happening with the data. But now, if I want to understand how do these regions communicate with each other, I again ask for the induced data flow. And let me just go for the simpler view. And so what I see here is that actually there is one region simulation time that takes the previous value of the wake music input. So if we want to see that here, for example, we see the current time is the previous value of a wake-up time. So because we use the previous value, we also draw a register here. And the simulation time produces a value current music, which is used both by set speeds and by the control motor unit. And this also produces a wake music value, and this also produces a wake music value, which again feed into the register. And so what this view tells you right away is that in this case there are no cyclic signal dependencies, no cyclic data dependencies. And also the layout algorithm here chooses to always put registers on the left. So meaning if all the leftward edges just feed into registers, then you see right away that here you do not have any cycle. And here we also have this coloring scheme of showing updates in green and initializations in black. So if both of these would be black, then we would have a problem, because they would both try to write different values to wake music, but because this is initialization and this is an update, we are again fine. Okay, and so this is one way of kind of blurring the line between control flow-oriented modeling and data flow modeling. Because usually if you look at this, and in particular this here, for example, then you would think, well, this is a classic data flow model. You would not think of this as a control flow model, even though we started from a control flow model. Okay, and we can also, this is what we just saw. We can also apply this to traditional data flow models. So for example, here we see a Listre program. Now in this case, with the state extensions as proposed by Jean-Louis Colasso and others in Marc Posé's group. So this is one example of where we have a mix of state-oriented and data flow-oriented modeling. And if we now look at this program, the question is, well, how can we derive an SC chart from that? And actually, that's something that Clément Pascotto from ENS, a master student with Marc Posé, has investigated in an internship that he conducted at our group. And so this is one result of an SC chart that corresponds to this data flow program. So that, again, is an example of showing how the line is blurring between data flow and control flow, that you do not really have to choose which one to model. They are really just two different views of the same thing, of the same model. And to this, you can, again, apply the data flow view, the induced data flow view that I showed earlier. Then you get, for example, a result like this, where, again, the registers are shown on the left. There you are basically back to something like you would also model in SCADE, except that we do it the other way around. We start from a Listre presentation, from a Listre model, and from that we derive this mixed data flow and control model, whereas SCADE starts from there and goes to the textual model. Okay, well, I started out with saying, well, we also want to allow the imperative programming style that we are used from C, for example, that we just use sequential updates. So since we allow that in our model of computation, we can also apply this to an original C program. So just like I showed from Listre, you can go to a C chart, you can also go from C to a C chart. And this is actually something that is in fairly high demand, for example, in industry. You have these millions of lines of controller C code that people want to visualize somehow. So, for example, from Bosch ETAS, there's a tool, eHandbook, which synthesizes visual SCADE models from C programs. And so we also do this for SC charts, except that I think we do it maybe in a bit more in a different way that also exploits a bit more the hierarchy of the original program. So if we just look at this little artificial program, C program, so for example, here we have this sequential update that is all happening instantaneously within a tick. It does not do anything useful, at least I don't think so, but it does things that would not be allowed in the traditional synchronous model of computation. Well, we can just transform it into in a C chart like this, where we start here, and the if statement corresponds to that. If A is greater than 4, then we do this, otherwise we do this. And again, this is just a slightly different syntax. So this actually is an entry action, meaning something that is performed whenever you enter a state. And now, just for this use case, we decided we do not want to have these entry keywords all the time, so we just hide them. So it's just a slightly different view, slightly more compact view. And just like I showed earlier, for example, you can collapse this or you can collapse this if you are just interested in certain parts of the model. So you can use the pragmatics features that I showed earlier just to explore a C program like that. And we preserve the structure of the original program, just like here, for example, the different indentations help your orientation. Here, the different superstate hierarchy levels help you with your orientation. And semantically, we do not have a problem with instantaneous loops, as shown here, because it's just all sequential. Another example, Fibonacci computation, is shown here. And in this case, we introduced a delayed transition here using a very simple scheme. Basically, whenever we have a cycle, then we put in a delayed transition. And if you do that, that means that you do not have an instantaneous loop anymore. And that means, this is just in a slightly different context. This is what you see here again. That means that you can produce data flow code from it. I don't go into the details now. But that means that, again, from this data flow code, you can synthesize a circuit. So in other words, we now have a way to synthesize hardware from C code. So that's just one more connection to this imperative programming, or to the traditional programming languages that were part of the title. Okay, so if I wrap up, so we looked at ScCharts. We have a very simple language with just 5 core constructs. We have a number of extensions to that. The model of computation is a conservative extension of the synchronous model of computation. It's still determined. We can model something like C programs, for example. And the compilation is done through a series of model-to-model transformations. And we have been using this now for a number of years also in the classroom. So if any of you might be interested, or you looking in the internet, you can just Google this and download this and try it out. And we try our best to support you with that. But there is still plenty of things to do. So for example, some variants of the model of computation, or the optimization of code generation, or for example, further improvements for schedulability analysis. So that is one thing. If you do something complex like the railway controller, it's still not easy how to make the things schedulable so that it is accepted by the compiler, so that it fits into this class of programs that I showed towards the beginning of my talk. And so that's something where we have some ideas, but we have not put them in. Okay, and that's what I had. And with that, thank you very much for your attention. Thank you.